In video 38 of Tensor Calculus, we pick up where we left off last time and complete the discussion of the Metrinilic property. This time, let's find the covariant derivative of our Kronecker delta function. Now, the Kronecker delta can be replaced by the dot product of our basis vectors. So this would be the same as the covariant derivative of zi, the contravariant basis vector, dotted with zj, the covariant basis vector. So this dot product is the same as our Kronecker delta. Well, now we just apply the product rule that we talked about in the last video. We'd start with the covariant derivative of zi, and then we will dot that with zj. Then we will add zi dotted with the covariant derivative of zj. And of course, from the last video, you know that the covariant derivative of each of these basis vectors is equal to 0. So that means that the whole thing has to be equal to 0. In other words, the covariant derivative of the Kronecker delta is equal to 0. That means that the Kronecker delta also possesses the Metrinilic property. Okay, well, what's the practical application here? Well, suppose we had something like this. Sj times the covariant derivative of a product of delta ij times Tm. Okay, well, normally, because we have a product here, we'd have to use the product rule. We'd take the covariant derivative of each factor, leaving the other constant, and add them together. But just like the example with the basis vectors in the previous video, the covariant derivative kills the delta factor because of the Metrinilic property. So all we have to do is to take this factor outside the covariant derivative. So we can move the delta factor outside. So it looks like this. And again, don't miss the fact that this is possible only because of the Metrinilic property. We wouldn't be able to do this for any other factor. But because it has the Metrinilic property, we can just take the delta factor out. And when we do, of course, this j index is absorbed, leaving us just with si on the outside. Okay, now what this means that we can always do this, and therefore we really don't need this intermediate step. You can see by inspection that this index will absorb this index even though these two factors are on opposite sides of the covariant derivative. We can see from this that this is going to be the case immediately just by inspection. Okay, well, it works the other way too. Suppose we had something like delta ij times the covariant derivative of tj. Well, because of the Metrinilic property, we can move the delta factor into the derivative operation. So it would look like this, delta ij times tj as a product. And of course, now we see that the j index is absorbed. And this leaves us simply with the covariant derivative of ti. And again, we don't need this intermediate step. We don't need to do this. We can see by inspection that this index is going to be absorbed with that one, leaving us with this expression. And we can see that directly just by inspection. And all of that is made possible by the fact that the delta factor possesses the Metrinilic property. Okay, well, now let's take the covariant derivative of our covariant metric tensor. That's zij. And this time what we'll do is to replace the covariant metric tensor with its definition, and that's the dot product of the covariant basis vectors. So we'd have zi dotted with zj, both covariant basis vectors this time. And just as we did before, we'll use the product rule here. So this is the covariant derivative of zi dotted with zj, and then the factor of zi dotted with the covariant derivative of zj. And as before, these two factors are equal to 0 because of the Metrinilic property, leaving us with the fact that this whole expression is equal to 0. So the covariant metric tensor possesses the Metrinilic property as well. Okay, well, as you might suspect, let's also do the covariant derivative of the contravariant metric tensor, and of course that's going to turn out to be the same thing, but let's just go through it real quick. That would be the covariant derivative of the contravariant basis vectors dotted with each other. This is something we derived back in video number 17. So the same sort of thing happens here. The covariant derivative of zi dotted with zj, and then zi dotted with the covariant derivative of zj. And of course, because of the Metrinilic property, these two factors, this one and this one, are both equal to 0, and that means that the entire expression, of course, is equal to 0. So we can say that the covariant metric tensor and the contravariant metric tensor both possess the Metrinilic property. Okay, well, what's the practical application this time? Well, remember we used these metric tensors to raise and lower indexes. So let's suppose we had something like this. We had Sm times the covariant derivative of a product of Zim times Tj. This is a product. And of course, normally we'd have to use the product rule, but because of the Metrinilic property, the covariant derivative will kill this metric tensor factor. So we can simply take this out as a factor outside of the derivative operation and express it this way. We'd have Zim times Sm times the covariant derivative of Tj. And of course, this combination of factors here will raise the index in S up into the upper position with an index of I. So this becomes Si times the covariant derivative of Tj. Well, because this always works, we don't really need this intermediate step. We can recognize just by inspection that this combination of factors, these two together, will cause the M index to be raised into the upper position to become I. So we can go directly from here to here just by inspection. And that's made possible because the contravariant metric tensor possesses the Metrinilic property. And it works the other way as well. Suppose we had Zim here times the covariant derivative of Tm. Well, we can move this factor of Zim into the derivative operation as a product of a factor. So it would look like this, Zim times Tm as a product. And of course, this operation will will lower the index for t back into the lower position and make it I. So this just becomes the covariant derivative of ti. And as before, we can skip the intermediate step. We really don't need this guy right here. We can see that the combination of this factor with this one will lower this M index into the I position to make it this. And that's made possible because of the Metrinilic property. Okay, one other example here. Suppose we had something like Si times the covariant derivative of Ti. Well, this time let's replace each of these individual factors with equivalent expressions. Si in the upper position is the same as Zi im times sm. So this contraction is the same as si in the upper position. And ti in the lower position is the same as tr contracted with z ri like this as a product. Okay, so all I've done is to replace si with this and ti with this. Now, because of the Metrinilic property, I can take this factor of zri out of the derivative operation and bring it out front like this. So this becomes zri times zim sm times the covariant derivative of tr. Well, the combination of these two factors together will simply give us a delta mr. Remember, the contraction of these two is, by definition, going to give us this delta factor. So that times sm times the covariant derivative of tr, and of course the m index is absorbed, leaving us with sr. And finally, we can rename the r index back to I, giving us si times the covariant derivative of ti. And you see what's happened here. We have managed to flip-flop these dummy indexes. We've lowered this index and raised this index to give us this expression. And of course, we don't need all this intermediate stuff. We know that this can happen every time. So what we see here is that the operation of flip-flopping dummy indexes, which is something we're already very familiar with, continues to work even though the factors are on opposite sides of the covariant derivative operation. And all of that is made possible because of the Metrinilic property of the metric tensors. Okay, the next thing I want to do is to introduce a new operation. Now, we pointed out a number of times that the covariant derivative always introduces a new covariant index. That's why we call it a covariant derivative. And you've seen how this works with vectors. We can combine it, for example, with a vector component like this, ti, a contravariant vector component forming this contraction is what we call the divergence of our vector t. Okay, well, this works because there's a contraction going on here. We have a covariant index here as a result of the operation, so we have to combine this with a contravariant vector component to get this to work. Now, what would happen if we were working with a covariant vector component? We couldn't form this contraction. So what I'm going to do is to define a new operation. We're going to say that this operation with an index in the upper position like this is going to be equal to zij times the covariant derivative with respect to j like this. We're going to call this the contravariant derivative. Now what the contravariant derivative does is it allows us to form similar contractions like this, only using covariant vector components. So watch how it works. You start with the contravariant derivative and contract that with a covariant vector component like this. Well, using our definition, that means that we're talking about zij times the covariant derivative with respect to j of ti. But because of the Metrinilic property, we can raise the index of t across this operation, and this is just equal to the covariant derivative of tj with the index in the upper position. And of course, we could rename j to I here. So the point is that these two operations, this operation right here is exactly equal to this or the same as this. So we can now extend our definition of the divergence to include this other form. We can say that it's equal to this, or it's also equal to the contravariant derivative contracted with a covariant vector component like this. And this same technique will work anytime we have a covariant derivative. In other words, what we've seen in terms of being able to flip-flop the indexes works here too. We can raise the index of our derivative operation if we lower the index of the operand over here. And that's a technique that's going to come in handy quite often. Of course, we could always just perform this operation every time we run into something like that, but this new definition gives us a very simple and concise way to deal with it. All right, I want to wind the video down with one final observation. So far, we've discovered that the covariant derivative of each of these objects is equal to 0. In other words, the Metrinilic property applies to each of these tensor calculus objects. Now, in future videos, we're going to run into some more objects for which the Metrinilic property applies, and I'll point them out as we run into them. But for now, I want to limit our discussion to just these objects. However, before we end this video, I want to make a particular point, and that is that each of these objects and all the ones that we run into in the future are going to be related either directly or indirectly to our metric tensors here and here. And of course, that's why we refer to this property as the Metrinilic property. So I've already pointed out that our metric tensors are roughly equivalent, at least from an information content perspective, to our basis vectors. I mean, that makes sense because this tensor is defined in terms of these basis vectors. It's just the combination of all the possible dot products between them. And the same relationship exists between this and this. So the information carried by the metric tensors is roughly equivalent to that carried in our basis vectors. So we can see immediately that our basis vectors are directly related to our metric tensors. But what about the Kronecker delta? How can we say that that is in any way related to the metric tensor? Why is it part of the metric family? Well, let's look at this. Suppose I had a tensor T mj, and I decided that I wanted to raise the index of m into the upper position. What would I do? Well, of course, I'd multiply, I'd form a contraction with the contravariant metric tensor of Im like this, and that would give us a form of T in which m is raised into the upper position and becomes I, and on the lower position we'd have a dot with j. Likewise, if I had a tensor T mj where both of the, well, let me make this I just to make it more consistent. If I had Ti like so, and I wanted to lower the m index, what would I do? I'd use the covariant metric tensor like this, and I'd use Jm, and that contraction would result in a tensor like this, a mixed tensor in which we'd have I and J like so. All right, we've done that many times. Well, now what I want to do is suppose we treat our covariant metric tensor the same way we treated T here. In other words, let's start with Z, M, J, and instead of thinking of it as a metric tensor, it's just a tensor. And I decide I want to raise the M index. How would I raise this M index? Well, I would multiply by Z, I, M. And if I'm just blindly applying the rules of raising indexes, I'm going to see this as a mixed tensor Z, I with a dot J like so. And likewise, if I treated our contravariant metric tensor as Mi like so, to lower the M index, what would I do? I'd multiply by this. I'd form a contraction of our covariant metric tensor with Jm, and that would yield a mixed tensor of dot I j like so. Now I know we don't need the dot right up here, but we'll leave it just to illustrate the point. Now because we know that both of these tensors, all of these tensors are symmetric, then that lets us express both of these as simply z ij. You remember that we don't have to use the dots when we know that the second rank tensor is symmetric. So what we've come up with there is a new item in our inventory, and we'd refer to this as the mixed metric tensor. This is our covariant metric tensor, this is our contravariant metric tensor, and this is our mixed metric tensor. It has a contravariant index and a covariant index. So let's add this to our inventory of tensor calculus objects. The mixed metric tensor Zij is equal to this contraction. It's Zim contracted with Zmj like so. Now, of course, you recognize that this is exactly equal to the Kronecker delta Ij. That's, after all, how we defined our contravariant metric tensor to begin with. And so what that tells us is that our new object here, the mixed metric tensor, is exactly identical to the Kronecker delta. So you can see now how the Kronecker delta is very much related to our metric tensor. Now let me point out that some authors actually go so far as to use this expression in every instance where I've been using the Kronecker delta. The two are identical to each other, and in some ways it makes sense to use this because it keeps reminding us that this whole relationship represents a tensor that we refer to as the fundamental tensor, and this relationship helps you understand why. Okay, I think that's a good place for us to wind this video down. Let's go do a quick recap. First thing we did was to determine that the covariant derivative of the Kronecker delta is equal to 0. And what that means is that the covariant derivative kills the Kronecker delta, meaning that it can move inside and outside the covariant derivative operation just as if it were a constant. That in turn means that the function of absorbing an index like j here works even though the Kronecker delta is on the other side of our covariant derivative operation. So this index j is absorbed to produce index I, just like this. It works just as if the covariant derivative operation weren't even here. That works in both directions. If the Kronecker delta is inside the covariant derivative operation, it can serve to absorb an index outside like this and turn this into Si. Okay, next thing we did was to determine that the Metrinilic property applies to both of our metric tensors. The covariant derivative of both the covariant and the contravariant metric tensors is equal to 0, and that again means that the operation kills these two objects and they can move in and out of the operation as if they were constants. That in turn means that this factor combined with this one can serve to lower the m index from m to I like this, even though the factors are on opposite sides of the covariant derivative operation. Works both ways. So if the metric tensor factor is on the inside, it can serve to operate on a factor on the outside. In this case, it's going to raise the m index, giving us Si on the outside like this. And that in turn means that the flipping operation where we move an index down and up on either of these two factors to produce Si and Ti like this works even though the two factors are on opposite sides of the covariant derivative operation. Now this led to the definition of a new operation that we call the contravariant derivative. and it simply gives us a mechanism where we can perform our derivative operation to produce a contravariate index instead of a covariate index. Now that means that we can extend the definition of something like our divergence to include this additional term. It's as if we're allowed to flip-flop the indexes between the operation and the operand like this, just as we did right up here. So this gives us a convenient means of working with a covariate object when that's more convenient than working with a contravariate object like this. And finally, we derived a new object called the mixed metric tensor like this, which we determined to be exactly the same as our Kronecker delta. And that in turn explains why the Kronecker delta is part of our Metrinilic family. It's really equal to this tensor, which is the mixed metric tensor. All right, with that, we'll bring this video to a close. Hopefully between this video and the last one, you've got a pretty good understanding of what the Metrinilic property is all about.